All right, thank you for the introduction. So I hope I can give everyone a short break from the column test and to understand the material behavior, especially the bond a little bit. So we are going to talk about the bond slip behavior under Flexure. So why we mean Flexure? It's brought up by our Bing-An test setup. So to understand the Bing-An setup, let's first envision we have a simply supported reinforced UHPC or concrete beam under 4-point bending. And then if we have a major crack in the middle, and then we want to understand how the reinforcement, the tension steel may develop at the major crack section. To understand that, we can take half of our beam and then replace the compression force in the compression zone by a support force and replace the tension force transverse by the reinforcing steel by the force that are pulled out by our actuator, so we can have a setup that can mimic the flexural stress states in a reinforced concrete or UHPC beam and understand the bond behavior under Flexure. So in our real test setup, we just rotate by 90 degrees for the ease of test. And for our test matrix, we have 3 different UHPC materials, the ductile and the UPF from King's Material, and 1 green ultra high performance concrete developed at UC Berkeley. So in this UHPC, we have 50% less cement content than typical UHPC commercial materials. And for fiber volumes, we tried 4 different fiber volumes, with major fiber volume being 1% or 2%, and 0 and 0.5 just we are investigating them for fun to see the effects of like lowering it to the minimum. And for the test age, our major test age is at 28 or 50 days, while we also tried early test age and later test age. The 100 days was mainly due to the pandemic and our lab was shut down. And it's an accident, not intentionally. And for the compressive strength, most of our UHPC tested were above 130 MPa and mostly between 170 and 190 MPa. And for the 3 days UHPC for the green ultra high performance concrete, the compressive strength is a bit low because of the low cement content. And for the bar diameter, we have from 16 to 32 millimeter to cover the major bar diameter you may see on engineering application, and the cover thickness from 16 to 51 millimeter to resulting cover thickness to bar diameter ratio between 0.8 and 3.2. And for the loading type, we have a monotonic test as well as reverse cyclic test to understand the bond behavior under earthquake. So that's about our test matrix. And also I want to emphasize that for all of our tests, no transverse reinforcement or no stirrups was used to enhance the splitting resistance. So all the results, all the splitting resistance come from UHPC and the fiber reinforcement itself. Now we can look at a few representative test results. First, let me present the monotonic bond slip behavior. So we see 2 types of bond slip behavior. The black lines here represent the bond slip behavior of UHPC without any fiber. So the fiber volume is 0 for the black lines, and the UHPC will behave very elastically until a splitting crack forms, and then we'll see an abrupt drop and then some residual plateau from the friction. So this is for UHPC without any fiber reinforcement, and you may not see any UHPC material actually. It's just presenting for fun. And for all other UHPC material, even with 0.5% fiber volume, we can see that the splitting crack was very well restrained after forming, and the UHPC can show a much higher bonding strength than non-fiber UHPC, and the failure was very gradual until a plateau was reached. And then I think we have a question previously about the bond performance of UHPC. So for all fiber reinforced UHPC, even 0.5% fiber volume, they are very ductile, and the bond strength is is above 20 MPa, and it's much higher than what we may see in conventional concrete. And then here I'm showing the crack pattern and failure mode of both non-fiber and fiber reinforced UHPC. So for non-fiber UHPC, as I mentioned, once a splitting crack forms, it opens unstably and the specimen just failed due to the formation of splitting crack. And then when we pull out the bar, there are minimum residual powder between ribs, showing that the failure was almost completely caused by splitting. Well, for all fiber reinforced UHPC, the failure was dominated by pull-out failure, so the splitting crack was very well constrained. It's like the crack width is very small, and after we pull out the rebar, we can see that the UHPC key between the steel ribs are completely sheared and crushed. They are like made into pulverized into powder, which means the failure was dominated by pull-out failure instead of splitting-induced failure. And then we want to present the impact of bar diameter. So here we show the bond slip performance of three set of specimens. So these three set of specimens have the same cover thickness to bar diameter ratio of around 1, but we increase the bar diameter from 16 millimeter to 25 to 32 millimeter to the blue line here. So with the same cover thickness to bar diameter ratio, we find out the pre-peak performance was similar across all specimens, but with larger bar diameter, such as the blue line here, the post-peak performance was more gradual than the specimens with smaller bar diameter. That is because the turning point or the end of the declining point was caused by a completely sheared of UHPC keys between ribs. So with larger bar diameter, the clear rib spacing was bigger, so it can sustain larger slips before the UHPC keys were completely sheared off. That's why for larger bar diameters, bond degradation may be more gradual than smaller bar diameters. And then we want to show the impact of cover thickness to bar diameter ratio. So here, for all the specimens, we have the same bar diameter of 16 millimeter, but from the yellow line to the gray line, we increase the cover thickness from 16 millimeter to 51 millimeter. So the cover thickness ratio was increased from around 1 to around 3.2. As we can see, increasing the cover thickness to bar diameter ratio, we enhance the UHPC bond behavior because the splitting was more well controlled with larger cover thickness. And if we plot the bond strength versus C to dB ratio, we find out that for both two UHPC materials, the bond strength was showing a linear relationship almost with cover thickness to bar diameter ratio. And then we want to show the impact of fiber volume. So here I show the bond slip performance of a UHPC specimen with 0.5% fiber volume represented by this black line, another with 1% fiber volume represented by this orange line. As we can see that increasing the fiber volume can slightly increase the bond strength because of the more controlled splitting, the higher splitting resistance as expected. And now we want to show the impact of test age and compressive strength. So here, like this blue line very low was green ultra high performance concrete. At 3 days, it has 25 MPa compressive strength. So this may be like what you may expect from a conventional concrete well confined, the bond split performance. So their bond strength was usually between 3 and 5 MPa. And for the other UHPC, if we increase the compressive strength from 25, I think this is around 150 MPa, it increases the bond strength to around 20-25. And if we increase the compressive strength to 190, increase the bond strength to around 30 MPa, and the decline is more gradual as well. And also another thing to note that, so for this green line and black line, these are two different UHPC material with almost similar compressive strength. As we can see, different UHPC material may show, if they have similar compressive strength, they may show similar bond slip behavior, which is expected and observed by other researchers as well. And now, if we plot the bond strength versus the square root of compressive strength, again, we see an almost linear relationship between the bond strength against the square root of compressive strength, which is similar to what we have observed for conventional concrete. And here we want to show the impact of reverse cyclic loading. So we have reverse cyclic load before peak as well as reverse loading cycles after reaching the peak load. So what we can see here is before the peak load, there is minimal damage in UHPC specimen. So the behavior was minimally impacted by the cyclic loading, basically following the monotonic curve. While after reaching the peak load during the descending branch, the reverse cyclic causes more rapid degradation or makes the bond stress decline more faster than compared to the monotonically loaded specimen. And that is caused by the reverse damage during the cycle. So if we envision that we are loading UHPC specimen from like origin 0, no damage, to point A when it reaches the peak point, and then we load it to point C. At point C, we may see some splitting crack as well as some crashed UHPC key between the ribs. And when we are reverse loading cycle, we'll first see a almost linear descending along with a sliding portion with very low stiffness, and the UHPC key will gain contact to the other side, and then until we reach point F and then to point H. At point H, the UHPC key was damaged again by the reverse cycle on the reverse slip end, and then there is more damage on the opposite side caused by this reverse cycle. And then if we want to reverse back to the original direction, and when the steel rib was get in contact with the UHPC key again, now the reverse cycle has caused more damage to the opposite side, so the remaining UHPC key was smaller than before the cycle was reversed, and that explains why we see bond strength degradation due to the reverse cycle. That's because the UHPC key was keeping damage due to the reverse cycles. So that's about all of our experimental results, and then we will move to our prediction model. So we propose a UHPC bond slip prediction model, basically made of first a linear ascending branch followed by a parabolic ascending branch, as well as a linear descending branch followed by a plateau here. And then we obtain the prediction equation for the UHPC bond strength, which is mainly related to the compressive strength as well as the ratio between the cover thickness and the bar diameter. We did not include the UHPC tensile strength here because we find out it impacts the bond strength, but we don't have enough results to include in the equation, so that may be included later. And the bonding stiffness and the slip at the peak was mainly related to the bond performance, the peak bond strength. And then we compare the bond slip behavior, the predicted against the experimental one. We find out the initial stiffness, peak strength, as well as the descending branch and the plateau was relatively well predicted by our model. And then we also go ahead and try the prediction model on other fiber reinforced concrete material found from literature. We found out our prediction model also predict pretty well about other fiber reinforced concrete material from literature. And then we know the bond slip model locally, and then we want to understand the behavior along the development length, where the bond stress or the slip may vary along the development length. So we use a partial interaction model, which basically means if you have a cutoff plane in a reinforced specimen and you want to understand the bond variation and the development length in the model, we can use this partial interaction model to understand the bond variation under a certain force, bond slip, as well as the cracking strength and matrix strength in the specimen. So I'm not going to overwhelm you by those mathematical equations. Let's just look at some major conclusions. So we find out to achieve a desired desired force in the reinforcement, there can be two different development lengths. The first is what we may usually talking about the minimal length that's needed to reach the yielding force of reinforcement. So when we are reaching the minimal length, the slip along, so the 0 means it at the cutoff plane, while if it's larger, it means it's moving further from the cutoff plane. So for the minimum length, the slip along the entire minimum length is large, which means the bond stress along the entire development length is very large. So the bond of the UHPC is fully engaged in this case. So we can minimize the development length needed for a certain force. And in this case, because the bond stress is large and almost uniform, then we can use a prediction model to predict the development length just by dividing the needed force by the parameter, the bar diameter, the parameter of bar, as well as the maximum bonded strength. And the second situation is about the minimized slip, which can be interesting because to control the cracking, we may want to control the slip of our bar along the development length. So to control the minimized slip, we may not fully utilize the bond strength of our UHPC. So in this case, we'll have a longer bonded development length when compared to the previous case of a small bonded length. And then by have a larger bonded length, the slip along the development length is much smaller, like around 0.1 to 0.2 compared to before 0.6 to 0.7. So at this stage, because the slip is smaller, the bond stress is lower than the peak, which means we did not fully utilize the bond stress of UHPC in order to minimize the slip. And then through mathematical derivation, we also propose the equation to predict the development length you needed to minimize the slip at a certain cross-section. And then, so this can be useful if one want to well control the crack width opening, so the steel bar can provide more bonding stiffness. And then we have a model for predicting the cyclic bond slip behavior, which is mainly based on energy concept to consider the degradation brought by different cycles. So under different cycles, we define a damage index, which is related to the energy. E here, E represents the entire energy that has been dissipated along all the previous cycles, while E sub 0 means the energy under the monotonic curve. So we represent the damage index by relating the energy that has been dissipated so far against the entire energy that can be dissipated through the monotonic loading, and we reduce the bond stress as well as the residual stress by this based damage index. And then we compare the predicted cyclic bond behavior against the experimental one for UHPC, as well as for another fiber reinforced concrete ECC, and we find out this energy-based degradation model will capture the bond strength degradation for different materials under cyclic loading. And here are the two papers that we published to present the results today. And in summary, we present the bond slip behavior of reinforced UHPC with different fiber volume, test age, material bar diameter, cover thickness, and cyclic loading. We propose a monotonic bond slip prediction model. We propose two different development lengths for either minimize length for yielding as well as minimize slip for achieving the desired force, as well as we propose a cyclic bond slip model to capture the degradation. And then at the end, I want to promote a special issue in UHPC related to bridge engineering. So it's a free open access journal published by Springer. So we are accepting papers related to UHPC application in bridge engineering in case you are interested in submitting your paper. So the submission is open from now until the end of this year. And then the paper will be published for free and it's open access. And with that, I'd like to thank you for your attention and be happy to answer any questions.